This is your actual sine wave, and this is a sampled version of your sine wave. And if you take more number of samples, I'm giving 2000, we'll see what we are getting. Yes. So you see how your sine wave is getting sampled into discrete time signal. So based on the number of samples, the sine wave is going to be sampled. Assume that in you know that in sampling frequency we have three cases, right? Undersampling, oversampling, and critical sampling. So what we have done here is critical sampling. Exactly, we have taken Fs is equal to 2000. So assume if I'm going to take Fs to be oversampling, I'm taking Fs to be 10,000. So we'll see what is the sample result. This is the sample result. Maybe if I can zoom it. You can see so many samples are there. So I'm going to define my sine waveform. Okay, so you can see the difference. And last case is undersampling. Undersampling means I'm going to reduce the frequency to less than 2000. So assume I'm going to have 500. Undersampling. Okay, undersampling, I'm having the frequency as 500. You see the waveform is not good. It's not actually a proper sampled sine wave. It's looking like a noise more or less, because the sampling frequency says the minimum frequency which you want to recover the signal from its samples is going to be 2 times Fs. And what people say, if you use the frequency to be more than 2 Fs, you can recover the signal even more in a very clear way. So we have seen 3 cases of Fs to be 500, 10,000 and 2,000, and we could find the difference only in the case where Fs equal 10,000, the signal was representation was good. Otherwise, it was looking more or less like a noise. Okay, so that is one thing we have to see when we are going to do sampling theorem. So 3 cases of sampling theorem we have seen. So I am just going to comment this code.